Okay, so is my screen visible to you? Okay, so this is the 12th class on electromagnetic theory, and today we'll be talking about antennas. And we would see that how the if you have a radiating source, based on how far we are from the radiating source, we can have different kinds of different field expressions. The electric field and the magnetic field expressions will be a strong function of how far we are from the radiating sources. So we will try to derive those relations and see so and talk about antennas. Okay, so that's about today's class. So to recall, we saw that when we had been discussing about electrostatics or magnetostatics, we discussed about scalar and vector potentials. And if you remember, one of the reason why we went to this, potential expressions like scalar potential or the vector potentials came up because it's easier to deal with these, right? So if you remember in electrostatics, we say that one is electric field and then we have potential, but because potential is scalar, it's easier to deal with potentials. So that's why we then first find potential and we see how we know that E is equal to minus grad V for electrostatic cases. And from there, we could find an expression for electric field. Similarly, when we spoke about magnetostatics, we saw that we have this vector potential, which we define as A, and curl of A is given as B. So this was about vector and scalar potentials, right? But now, if we look at the Maxwell's equations and try to write this Maxwell's equations in terms of the scalar potentials and the vector potentials, scalar and vector potentials, how do they look like, right? So basically why we are doing this is we will go to the concept of a dipole, of a radiating dipole, and we will try to write the electric and the magnetic field expressions at a certain distance from this dipole, and we want to see how the expressions look like, but we want to derive them in terms of this scalar and vector potentials. Okay, so that's why first we will try with writing the Maxwell's equations in terms of the scalar and the vector potentials. Okay, so here what we do is that uh, if you look at this expression, here we put, if we put B as curl of A, this is what we will get, right? And now we can take the, so E plus del A del T. So if you take this to the left hand side, you get an expression like this. Now from vector calculus, like vector algebra relations, we know that if curl of a certain quantity goes to zero, one can write this quantity as some gradient of a scalar function. Okay. So because we know that E is again related to minus grad V in electrostatic case, so here we can say that in this case, E plus del A del T can be written as minus grad V. So it's important to note that when we talk about, we want to finally find electric field and magnetic field intensities. So those are our observables, or those are the important physical quantities. The absolute value of the scalar or the vector potentials is not that important. Okay, so we know, like if we talk about potentials like scalar potential, maybe we know that the absolute value of scalar potential does not matter. The absolute value of V does not matter. One can add some scalar to it, right? That will just be you can say shifting of the origin kind of thing. So that does not matter. What matters more is how much is the change, or what is the potential difference, right? So, and that potential difference, or this gradient of V, is again related to the electric field. So in a way, in physical world, what is important to us is this field intensities and not the absolute values of scalar and the vector potentials. So one can define the scalar and vector potentials in such a way that are physical quantities, that is the electric and the magnetic fields. Those terms are, those are, you can say, so in a given quantity, that should be well defined. The electric field and the magnetic field should be well defined. We can work with changing the potentials expressions as long as this intensities, field intensities do not get affected. Okay, so that's what we will try to do in the coming slides. So for here, what we have done is that we have written E in terms of, so the expression here gives us E in terms of the potential, like the scalar potential and the vector potential, right? And now if we talk about electrostatics, then this term would go to 0. And what we will get is just minus grad V, which is the case as we had in the electrostatic case, right? Now, another thing is, so the potential expressions, that is here, if we have these expressions that we have, B equal to curl of A. So that is the relation for how B is related to the vector potential. And this is the expression for the electric field. So now we know how the electric field and the magnetic field can be written in terms of the vector and scalar potentials. So given this, now if we put this expression, so we know what is E. So if we put it in this, the first Maxwell's equations, we get an expression like this. And here again, you can see that if one considers the case where divergence of A goes to 0, we would get back the Poisson equation, right? Which is the static case. So everything is consistent given the conditions that we impose, okay? And this is the expression that we get by replacing B and E in the fourth equation here. If we do that, we get an expression like this, and you can see it's quite complex expression, right? So here, this term here, the first two terms is like the wave equations, but this additional term is a complicated term. So it's not very easy to just find out A from here, like not a easy differential equation to solve, right? So we would now see if there is a way of choosing A and V, because we have the freedom to choose the potentials in such a way that simplifies our life, right? So we'll try to choose A and V in such a way that our equations get simplified as long as the electric and the magnetic fields do not change. Okay, so that's what we'll try to do next. So, but till now, what we have tried to do is we have tried to write electric and magnetic fields and the Maxwell's equations in terms of the scalar and vector potentials. Okay. Now, gauge transformation. So this is what I was talking about. So we will try to simplify our expressions by making some choice about our potentials. Okay. Keeping in mind that the electric and the magnetic fields should not change. So here what we can say is that suppose we choose a new vector potential A prime, which is given as A plus some alpha. Okay. And we choose a new scalar potential V prime, which is given as V plus some beta. Okay. Now, we want the electric field and the magnetic field to be same. So that means when we do a curl of A prime, so curl of A prime should be equal to curl of A, so that the B remains same. So which means that curl of alpha should go to 0. Now we know again that curl of gradient of a scalar quantity is 0. So one can in principle write alpha as gradient of some scalar quantity lambda. Okay. So this is a general form. Now, talking about electric field, we also want to have the same electric field, right? And we saw that the electric field has this expression, right? So now you know that to maintain the same expression of the electric field, this term here should go to 0. So from here, you have now found another expression which gives us the relation that beta has to satisfy, right? So if alpha has this form and beta has this kind of a form, A prime and B prime is related to A and B by this relation. And if we have such kind of a, if we do such kind of a transformation, so if the initial vector potentials and scalar potential was A and B, and if we add certain terms which are of this form, we can get to new vector and scalar potentials such that our physical quantities or the field intensities remain identical. So this is allowed. This does not change the physical situation. Okay. But now one can choose this lambda, or this terms in such a way that our expressions get simplified. So that's the use of having gauge transformations. Okay. So one can choose different kinds of gauges based on what we want to do, and different gauges can have different, advantages. Okay. So we'll talk about some very popular gauge in the coming slide. And in magnetostatics, we do choose A such that divergence of A goes to 0, right? And this is what happens. So if you put divergence of A to 0, we get the Poisson relation. Okay, so now let us talk about two very popular gauges. So first is the Coulomb gauge. So this is this gauge where we choose A such that it is divergence-less. Okay, and if we do that, we get the much simplified version, which is the Poisson equation. And from here, we can try to write an expression for the potential. This is something which we had done when we were talking about electrostatics and magnetostatics, right? So this is a very simplified version given in comparison to what we had before. So if you are asked to solve this, obviously, if this term goes to 0, that simplifies our calculations, right? So this is one thing. Another is this, right? So this is the scalar potential. We also want to find the vector potential. But when you find the vector potential with this gauge, you see that it's still not very easy to solve. So you have so many terms, and it's not a very easy differential equation to solve for A. So Coulomb gauge does not make things very easy when we have to find the vector potentials. For scalar potentials, it works fine, but for vector potentials, it's not that useful. So there we choose another gauge, which is the Lorentz gauge. So here what do? We choose an A such that divergence of A is given as minus mu naught epsilon naught del V del T. How do we get to this term? So if we go back, we had this expression, right? So now if we want to get rid of this term, one has to have A such that divergence of A is equal to minus of mu naught epsilon naught del V del T. So that's the condition which the Lorentz case uses. Okay, so then this term goes away and we are just left with the wave equation, right? Only this wave equation term would be there, and that would simplify our calculations. So that is what Lorentz gauge does. So if we give this condition, we get an expression for A which looks like this, and this is how the expression for V looks like. So you can now see that the virtue of Lorentz gauge is that here V and A are on equal footing. So you can see that both of them have this similar form, right? You have this wave equation form on one side, and so these are analogous equations. So now one can choose a new differential operator, which is given as del square minus mu naught epsilon naught del square del T square, which we call the D'Lambertian operator. And if you do that, this is the simplified version of the expressions that we get. Okay, so this is what we get from the Lorentz case. Now, one interesting point about this relations is that, so if we talk about how our Poisson's equations look like, or if we look at these expressions, and from here, if we try to find an expression for V and A, this is how it looks like, right? This is from not well known, or this is something which I've already discussed. But one important point to note here is that this is valid when your things are like your potential, or your current density, or your charge density, when these things are not changing with time. If you have a time varying thing, then these equations need to be, there has to be a very, you can say, subtle change in this relations. Why? Because suppose if you have this expression, so rho is the charge density at a certain point of time. At some later time, if your rho changes, that would not be immediately reflected in the potential. Why? Because we know that electromagnetic waves travel at the speed of light. So at least it should take some time for the information about this change to propagate to our field point, right? So that's why what we have is this retarded time, which takes care of this propagation time that is required for the electromagnetic wave to propagate. Okay, so that means if certain change happens here, it takes a finite time, which if it is in free space, it would be given as r by the speed of light, for the information to, for the information of this change to actually reach your field point. So that's why what happens is that now when you write the expression of potential, or the vector or the scalar potential at a given time, depends on the volume charge density, or the current density at some time which is earlier, right? And so you have this TR time coming in, which is given as T minus R by C. That means any change that has happened at a time slightly before actually impacts the potential that you see at the instant t. And how much before will be given by what is the distance between the the source and the field point, and what is the medium in between. So what is the speed of propagation of your wave, right? So if it is in free space, it would be given as R by C. So T minus R by C is TR. So the potential, the surface or the volume charge densities or the current densities at TR affects the potential or the vector of the scalar potentials at time t. Okay, so this is why these are called retarded potentials, because something which has happened before is affecting the current potentials. Okay, so this is important to remember, because when we talk about a radiating source, so there'll be certain changes in at the source, but that would not be immediately reflected at the field point. It would have a valid finite time interval for it to propagate. So now let us move to the Hertzian dipole antenna. So here what we are talking about now is a radiating dipole. Okay. So suppose if you have some dipole at a point and you say that what would be my electric field or magnetic field at a given point somewhere at some point, okay, P. What would be my field intensities at this point? So how do we get to that expression, right? So here also what we'll try to do is we'll try to first find the expressions for the vector and the scalar potentials, and from there try to derive our expression for the field intensities. Okay. So if you have some dipole, okay, so here when you have a dipole antenna, you can consider it to have some current flowing through it and some dimension. Okay. And delta Z is considered to be much, much smaller than the distance between this dipole and the field point. So if it is in this, if this condition is valid, in a way, we can consider it to be a the exact, what do I say? If it is comparable, then what happens is, the dimensions do play an important role. When you can yes. So yeah, some issue with my phone and the network. Yeah, okay. So now, if we look at the expression for, look at the expression here for uh, the vector potential. So you see that there is a current density involved, and it's over a region. So you have a d tau, that is a volume element involved in this integral, right? So now in this case, what you can write is you can consider a current I flowing through this dimension of delta Z. So you can replace J del V as I del Z. Okay. And here we are considering it to be along Z. So you can just write it as I delta Z, Z cap. Okay. And to simplify the calculations, one can consider it to be at the origin. So R prime is taken to be 0. So now we need to find A first. So how do we do it, right? So this is our general expression of A, right? This is what we have from here. So now here, what we have to do is, because your current is flowing through in the Z direction, we know that the direction of A comes from the direction of J, right? So now, yes. Any questions, guys? Okay, I consider it skip. Here, what we are going to do here is that, so the dimension direction of J will be reflected in the direction of A. Okay, so because your current is along, or your J is along Z direction, your A will along Z direction. And now, if we want to move from the rectangular coordinate system to spherical coordinate system, we know that if your vector is along Z, there is no component in the phi direction. So your A phi goes to 0. So now, based on what is your angle, in like once you do the transformation, you can write the radial and the theta components as Az cos theta and minus Az sin theta. Okay. So once you do that, so now if you change your coordinate systems, you would have a term like this. And here you can see, you can take this terms out of your integral, because it does not depend on delta Z, right? So you would have finally an expression like this, where I is the retarded current, which is given as I e to the power minus beta r. And what is beta? Beta is basically related to the wavelength of your wave. Okay. So if you now include the time, the change in time, or the time basically variation, so there you'll have I as I e to the power j omega t minus beta r. Right? So you have a omega t term. So omega takes care of your frequency, and you have the beta r, where beta takes care of your spatial periodicity, which is the wavelength. Okay. So this is your retarded current. And there, when you write T, so now if you expand it further, you would see that you will have this T minus R by C. Right? So this takes care of your time delay that is inherently involved in the signal to reach from your source to the field point. So that means this is how your expression of Az will look like. And then you can move to the radial coordinates by using this relations. Okay, so this is how it will look like. A phi will go to 0. So now, once you know the expression for your vector potential components, you can try to find the magnetic field just by doing a curl. Okay, so B is equal to curl of A. So the field intensity A should be given as 1 by mu naught curl of A. Right? It is for free space. For a particular medium of a given permeability, it will be given as mu here. So now this is just normal curl. And if you, these are just calculations with some rearrangements to simplify the expression. So what's interesting here is that now you have two terms. So one term you can see goes as 1 by r, other term goes as 1 by r squared. Okay, so this is telling you that based on how far you are from the antenna, different terms will be dominant. Okay, so at a very far distance, you would see that this term 1 by r term will dominate, where close to your, as you come closer, 1 by r square will gradually get dominant. Okay, and once you find h, we know how h is related to your electric field. And so you can try to find an expression for the electric field, right? And this is how the electric field components will look like. And here you see, again, you have 1 by r square term and 1 by r cube term, right? So that means when you come very close, you can understand that this r cube will gradually become very important, right? The electric fields will then gradually become the dominating factor, right? So now, if we look, region wise, so if you consider at very far distance, your er goes to 0, but e theta, you can see, has this so basically here you can see the 1 by r square and 1 by r cube will be negligible, but this term will remain at a very far distance from your dipole. So you will have the e theta component. And again, if you look at this expression, this term will survive while this term will be negligible, right? So all the 1 by r terms will remain in the far field region. Okay. So now if you try to find an expression for the Poynting vector, so that would have this E cross H star, right? So that means you will have a 1 by r squared dependence. And now if you want to find an expression for power, you do an integration over the surface area. So that means it becomes a constant quantity, right? So it's a constant average power that is radiated from the antenna. So if you are sufficiently far from the antenna, you would see that the power density, if you find the net power that is radiated from it, will be a constant quantity once you do an integration for the entire surface. Okay. Another thing is the near field. So near field case means you are very close to the antenna. Now we will talk about this fact is how far is far and how near is near in just a few minutes. But consider the case where you are very close to your antenna. So there again, 1 by r cube will dominate. And you can see here, so if we go back, all of these terms will be negligible. So there, this terms would go to 0. So in a near field, it's the electric field which will be dominating. Okay. The electric field will be dominating while the magnetic field will be close to 0. So you can try to write an expression for the radial and the theta components specifically. And this is actually the dipole equivalent, right? Another thing is, so this is very far, very near. Now there's an intermediate region where 1 by r squared dominates. And when will that happen? So that will happen when BR, so you have this term here, right? E to the power minus j beta r. So when the beta r term is close to 1, that means when r, which is the distance between the antenna and the field point, is comparable to 1 by beta. That is when it is comparable to lambda by 2 pi. And 2 pi is 6 to 6, so it's lambda by 6. So when we are in this region, it is the intermediate region where 1 by r square dominates. Right? So here what happens is this e to the power, this term would go away. So there it's actually not radiating power. So these are called inductive fields. Okay. So now in questions, there could be questions where you are asked, what is the far field regime and what is the near field regime, right? So how do we define it? So we define it in terms of this term here. So if your R is such that, so when it is much larger than 1 by beta, then it's in the far field regime. When it is much smaller than 1 by beta, then it's in the near field regime. And when it's comparable, it's the intermediate regime. Okay. So this beta will again depend on the wavelength of your wave. Now, the dimensions of the antennas do play a role. So here, if your dimensions of the antenna becomes comparable to the wavelength, so then, the dimensions would play a role. But if it is much smaller than, or if you are far, the wavelength is far larger than that. So in that cases, that does not matter. The dimensions do not matter. So if the radiation or the Fraunhofer diffraction region is termed as the fact where the distance from your field point to the source point is much greater than 2d squared by lambda, where d is the dimension of your antenna. And this is another important thing is that if you try to find an expression for the power, so this is nothing but the Poynting vector, and now you're trying to do an average of the Poynting vector. So you write the expression for the electric field and the magnetic field and do a cross product. And this is how the expression will look like. So you can see this sine square theta coming up here. Okay, so it does have a theta dependence when we look at the average power that is radiated. Okay, so now if you choose a range of your theta, so this is the Poynting vector, and now if you write the power, so then you have another r square sine theta d phi multiplied to it, and that gives you the sine cube theta dependence. So if you are having an antenna, that means you on the based on what angle you are from your antenna, you would have a power dependence which would be given by the sine cube theta term. And if you integrate over theta and phi, that would be the total power. So once you do the integration, you get an expression like this. So this is the total power radiated. And you can see there is no radial dependence here. So it just depends on the current that is flowing through the antenna, the dimension of your antenna, the wavelength of your signal, okay, and the medium. So eta naught here is the wave impedance, right? So it's given as 377 ohm when we talk about free space. If you are in a different medium, you would have a root over mu by epsilon multiplied to it. So the medium does play a role. And these are the factors on which the total power radiated depends. So here you can see that you can just write it in an analogous form as I square R, where this, which is equal to PT. So you can see whatever terms are coefficient of I square will actually be, analogous to a resistance. So that is what we call the radiation resistance. So the radiation resistance expression will be given as eta naught by 12 pi delta Z beta whole square. Okay. So that is your radiation resistance. So that again depends on the medium that you are in, the dimensions of the antenna, and the wavelength of the signal that is being propagated. Okay. Ideally, like what it means is that you are considering the antenna as some resistor, some effective resistor. So now based on the different, the dimensions of the antenna and the wavelength of your the signal that you are trying to that is being radiated. So your expression for the radiation resistance would be given by these different relations. And this is a very good book by so Cross and Balanis. So this is, I think this is also what was suggested in the class. So this book, there's a book which deals with all the derivations of how you get to these expressions. Basically, there you have to consider based on how big or small your antenna is. You have to be careful about talking about the dimensions of the antennas in certain cases. In such cases, you might not have to. So now, based on, there could be direct questions where you are said that you know the length and you know the wavelength, and you have to find the radiation resistance, or you have to find the power. So in order to find the power, you have to find the radiation resistance. So there you can use these relations. You can see it depends on the ratio of the length of your antenna to the wavelength that is being radiated. Okay. So this is a typical question which, so here it says that a magnetic field strength of 5 microampere per meter is required at a point. So theta is specified and the distance is given as 2 kilometers from the antenna in air. So the medium is specified. Now it's said that neglecting ohmic loss, the power transmitted by the Hertzian dipole antenna of length lambda by 25 is how much, right? So that means we know that at a distance of 2 kilometers and theta equal to pi by 2 from the antenna, the field intensity is given by this expression here, 5 into 10 to the minus 6 ampere per meter. Okay. So your delta Z is given as lambda by 25. So that means you can understand that we are in the far field regime. Your delta Z is much, much smaller than lambda by 2 pi, right? Lambda is given by this term here, right? Lambda, it's much smaller than lambda by 6. So that means you are in the far field regime, and there you have to consider this expression of your magnetic field. Okay, so you have just 1 by R term here. And now you put the expressions like substitute all the conditions that are already specified to find an expression for the current. Your H phi is given, your delta Z is known, lambda is known, R is known, so you have to find the current. So this is the current that is flowing through your dipole antenna. Now, once you know the current, it is said that what is the power transmitted. So now you know the expression for the power, right? It's given as P is equal to I square R. And here, so as you can see, you know I from here, and the R is the radiation resistance. So this is the relation that we have used, right? So you can see in this case, your L is much smaller than lambda by 4. So you can use this relation. And if you do that, this is how your expression of your power would look like. Okay, so there could be questions in the similar fashion. So based on the same expressions that you have. So now if you were in the near field regime, then your expression for the radiation resistance would vary. Your expression for the magnetic fields would vary. Okay. Now, this was another question in the last year's assignment, which said that there's a Hertzian dipole which operates at some frequency, which is given in free space, and the dipole dimensions are given, the current is given. So what is the approximate near and far field domains? So how do you find it? So first you see that what is the wavelength of your wave that is being propagated. So you know it's in free space. So the speed of light, speed of the wave is given as c. Okay, and you know the frequency. So c by f will give you the wavelength of your wave. Right. So now once you know the wavelength, you know the dimensions. Right. So now you can see that you have to use this relation, which is given as r equal to 1 by beta. Okay, so when r is much smaller than r by beta, it's the near field regime. When r is much greater than 1 by beta, it's the far field regime, right? And beta is given as lambda by 2 pi. So you have to find the value of lambda from the frequency, okay, and use this relation. So that would give you the answer for this kind of questions. Okay, now what the next question could be that given this, if you are asked to find an expression for the uh, the field intensities in the near field or the field intensities in the far field. So there again, you have to choose the expression of your field intensities based on which region you are in. So if you start with the very basic expression, you would have both 1 by r and 1 by r squared term. Now, if you are in the far field, you have to you will only have this term. So this term will be negligible. Otherwise, you will have the 1 by r squared term. So based on which regime you are in, you have to choose the expression of your electric field. Okay, electric field and magnetic field. So another question of these are very standard questions just based on whatever concepts we just discussed. So if you have any doubt, you can ask me. So here, what we see is that this is a short dipole antenna. The length is given, the current is given, and it is said that the dipole is used for cellular, the telephone communication and radiates at this frequency. The frequency is given. So you have to find the total power radiated by the dipole in free space. So that means you have to just use this expression, right? So you know it's in free space. So eta naught is given 12 pi. Your current is given. Delta Z is given. The frequency is given. So you can find the expression for the wavelength, and where beta is equal to lambda by 2 pi, right? So by using this relation, you can try to find the expression for the total power that is being radiated. Now, next part of the question says that if now it's not in air, but in water, okay, how much of the current is required to maintain the same power? So there, what is important to note is that mu is equal to mu naught and epsilon r is given as 81. Sigma is 0. That means it's not a conducting medium. It's just, so see, conductivity is negligible, it's considered to be 0. Only mu and epsilon r is given. So where will it be used? So this term will change. You will have eta naught, which is the wave impedance, only in free space. When you are in a different medium, your eta naught will be changed as eta naught into root over mu by epsilon, right? And because mu is equal to mu naught, that means here this term will just be changed to eta naught by root over epsilon r, right? Because if you remember, the wave impedance is just given as root over of mu by epsilon, right? So now here in this case, mu is same as mu naught, but epsilon has this 81. So it would just mean that now in your expression of the power, you have this root over of 81 multiplied to it. That is 1 by 9. Right? Now, what must be the current in the dipole to maintain the same radiated power? Okay, so that means here you have, in this case, this term has got a, where is my pointer? So this, you will have an extra 9 coming in here, right? Now, because you have an extra 9 here, that means you would need less currents here as well, right? So the current will then be reduced to root over of 9 because you have I square here, right? So that means you need less currents in water to maintain the same radiated power. Okay, so that means whatever current you had here it will be replaced by root over 1 by root over 9, which is 2 by 3. Okay. So that means when you are in a different medium, the wave impedance changes, and that's why the current that is required will change, or the power that is generated will change accordingly. Okay. So that's how this type of questions can be answered directly from the equations that we had derived already. Okay. So that's it. Do you have any questions regarding this?
मैम ये शॉर्ट डाइपोल वाला जरा एक बार फिर से बता
Yes.
First one question once again. Please give a hint for this question. A short dipole antenna is 10 mm long and carries a current up to M.
This one, right? So
Yeah.
what are the information that is provided? The dimension of your dipole is known, the current is known, and the frequency is known, right? Now, if the frequency is known and it's in free space, what is the relation between the frequency and the wavelength? So it's related by the velocity of your wave, right? So V is equal to C into lambda. We know that, right? Hey, what am I saying? V is equal to, so for any medium, we know that. So if it is in free space, it would be given as C. For some other medium, it would be given as the velocity at that medium. And that is given as nu into lambda. So what is nu? Nu is the frequency and lambda is the wavelength. So now in your question, you know it's in free space. So this is C, 3 into 10 to the power 8. And you know what is your frequency, which is given as 900 megahertz, right? So that means you can find an expression for lambda, right? Now, once you know the expression for lambda, if we now go back to the expression of our power, right? So which is here. So here you can see, I lost my, so here you can see that it's in free space. So eta naught is given as 377, right? You have a 12 pi, you know the current that's given in your question, you know delta Z, which is given in your question, and you know what is beta. Beta is given as lambda by 2 pi. And lambda you can get from the frequency, right? So now you know all the terms. So you can use this relation to find the total power. Is that clear?
Yes, clear.
Yeah. Okay. So is there any other question? Okay. So if not, thank you. Basically, these were the relations that I was talking. Yeah. So thank you. I think this is the last class of our of this course. We might have a extra class, which would be more like a summary class of whatever we had discussed over the entire course, during the entire course. And I hope this, like the entire session, has been useful to all of you. So all the best for your exams, and thank you.
Thank you so much, ma'am.
Yeah, thank you. Thank you.